Well, thank you very much indeed, Connie and Thomas and everybody else for your kind invitation to make my very first visit to Louvain. And I enjoyed it very much. In particular, this afternoon, I was able to see the exposition to the end of time, which if any of you haven't seen that, I strongly commend you. It's full of very interesting historical displays as well as art with which it merges very well. So Thomas and his colleagues deserve a lot of congratulations for this. I should also say thank you very much for the Solvay family for their ongoing active participation in and sponsorship of the Solvay program, and I'm here, thank them, and I'm very glad that Marina is here, and Jean-Marie and Marina and Mimi were at the presentation this afternoon, and they enjoyed it every bit as much as I did. So thank you very much indeed, and thank you for your kind introduction, Connie. The topics you mentioned are in fact ones that I'm going to try and talk about in this lecture. And I'm going to give a sort of an overview, if you like, and then I believe there's quite a bit of time set aside for questions, and that will be an excellent opportunity to go dig a little deeper into some of these topics. So this will be very much a sort of general semi-popular overview, and it'll be somewhat broad, and my goal in this talk is really to try to convey some of the excitement in what I see as a sort of rather large area of discovery going on right now in astrophysics. And I call it extreme astrophysics because the topics that I'm going to highlight here are ones that are, in some sense, pushing the technology, pushing to the edges of what's been done before, rather than doing old measurements in a better way. They're really opening up new territory. And so it's in that sense it's extreme, and I'll try and communicate the range of astrophysics. So if I take this is sort of my overview or synopsis, if you like, is that I'm going to say a bit about the, that's that one there, just the reach of modern astronomy, and bring out this idea that there's new territory out there being explored as we speak. Then I will mention the next two topics are ones that were Connie mentioned, relativistic jets and spinning black holes, and I've got back into this business because there's been a lot going on observationally, and then the same is true, I think, for cosmic rays and shock fronts. So I'm going to say a little bit about that. And then finally, I'm going to talk about a topic that has become hot, if you like, in the last 2 or 3 years, and it's really only been around for 10 years or so, and that's the idea of fast radio bursts. So those are the 3 examples of rapidly developing sort of subfields of astrophysics. So let's start, and this is very much a general overview to try and convey some of the range of contemporary astrophysics. So, or astronomy, I should really say. So astronomy, of course, has its roots in optical astronomy, people using their eyes or eventually telescopes like that to look at the sky using the visual band. And as every physicist here knows, that's about 1 octave in, wait a minute, yeah, let's go back. Right, it's about 1 octave, that's what I was supposed to press. And if I represent this by 1 octave on a piano, then we've got the sort of typical optical spectrum. Now, if we can look at that with Hubble. We can look at it with the VLT, which is an interferometer now for 4 telescopes operating in Chile, a European operation that's been remarkably successful, and I'll come back to one of the things it's done. And then next, there's James Webb Space Telescope, which we hope very much will be launched on December the 16th after rather a long hiatus. The previous launch date was Halloween, and for some reason it was decided that was not such a good idea. And so it is now being launched, I hope, on December the 16th, and it's going to be followed by, I think, what we call as 6 months of terror, because it's got to get out to its observing place at the second Lagrange point. It's got to have all of these moving parts unfurl perfectly, and it's got to have all the electronics and all the communication and everything else all work. Now, a lot of very clever people have been working on this, but it's everyone's going to be on the edge of their seat watching these things happening. But by June next year, we hope we will be seeing spectacular images that will be as transformational for astronomy as Hubble was. So if we now go on, so if we just look at James Webb, of course, is an infrared telescope, but if we just talk about optical astronomy, there's just one octave out there to explore. Now, as you all know, there's the whole electromagnetic spectrum there, which you can display as 10-gram pianos. And so there we see just the one octave there, and it goes from the lowest frequency radio waves to the highest energy gamma rays. And we go from waves to particles, as all the physicists here will be keenly aware as we talk about this. And they're the different spectral bands. Gamma ray astronomy counts for a lot of this, but not all octaves are equally productive of physics or science. Gamma ray astronomers boast their 4-gram pianos worth, but there's an awful lot going on in the optical band, and it's not a coincidence that that's what we look in. So, but nonetheless, there's a lot to explore, and most of this is being actively explored. That's the remarkable thing. Here's a low-frequency radio telescope out in Holland, LOFAR. There's a highest energy gamma ray facility on the ground. This is LASSO, which I visited in western Sichuan near Tibet, and this is a spectacularly successful thing. It's making discoveries by going up to the highest end of the gamma ray spectrum. And here's the Event Horizon Telescope, which I'll say a little bit more about, which uses millimeter waves interferometrically to get the enormously angular resolution. I'll say a little bit more about that. And if we look at the whole electromagnetic spectrum, in the roundest numbers, there's about 70 octaves of spectrum available there. And astronomers are using this and combining data throughout the whole spectrum. If we go on, it's not just electromagnetic signals that we're looking at. We're also looking at what's sometimes called multi-messenger astronomy, or particle astronomy, and the oldest one, of course, is cosmic rays, and I'll say a little bit more about these. These are particles which come from the sun, come from the planets, but particularly come from the galaxy and then beyond the galaxy. And I'll say a bit more about this in my second topic. And again, we have a large spectrum there to explore. And sorry, that's one spectrum there. And a common physics unit, as the physicists here will be, and other scientists will be aware, is the Electron Volt. And so chemists are typically dealing with it, regular chemists are typically dealing with electron volts as the unit of energy. But if you take cosmic rays, they go up to more than 1 electron volt, a zeta electron volt. And a zeta electron volt is 10 to the 21 electron volts. So we'll come back to that point. That gives you the range that we're talking about in terms of the energies of the individual particles, the photons, the protons and nuclei that we're talking about here. So if we go on, so there's a cosmic ray detector. This is the Auger facility in Mendoza County in Argentina. Spectacular place, but also a spectacularly successful observatory, and its speciality is looking at the highest energy cosmic rays right up here at the end. So here, if we add these cosmic rays in, that gives us 110 octaves to explore. And if we now go on, we can add in gravitational radiation. As you will be keenly aware, that now becomes a channel for making astronomical observations. And this is sort of roughly the spectrum being explored. Not saying the detection over all of those sources, but there's a lot that's going on individually. And if you ask where it's being explored, the lowest frequency gravitational waves are the cosmological ones, and these are at zepto electron volts. The going from lowercase to uppercase is if you make that mistake, you make an error of 10 to the 42. So a zepto electron volts is 10 to the minus 21 electron volts, and that's the lowest energy graviton. If you want to call it as a particle, you call it a graviton, and so down there in terms of energy. And here is the Virgo contributor to the International Network of Gravitational Radiation Detectors, and that's brought us up to 130 octaves to explore. And then if we go to my final slide in this lot, we can throw in the neutrinos, and the neutrinos have been sort of in astronomy for a long time, from knowing that how important they are in detecting them from the sun, also from a nearby supernovae called supernova 1987A, and that doesn't go to quite such large energies as the cosmic rays, but it still goes up to pretty high energies, and again, that's very much an active area of research. Here's one facility. This is called IceCube. It is a major astronomical observatory mounted at the South Pole. So it's at the South Pole, and it is exploring astronomy using neutrinos, but it is also doing fundamental physics using neutrinos, because you can explore the unknown properties of neutrinos can be explored using experiments performed with a facility like IceCube. And I'd like to show this one here because the leader of this project is Francis Halzen, who was a graduate student here in the days of Lemaitre, and is a proud Belgian, but he doesn't go to the South Pole because there are no good restaurants there, so that's the giveaway. So if we add that in, we're now up to about 140 octaves to explore. So there's a lot going on in astronomy, and I like to say that even third-rate scientists can make discoveries with these opportunities in front of them, and astronomers are first-rate scientists. Okay, so the whole thing put together, we call that nowadays multi-messenger astronomy. It's a 20-year-old slogan, but it really is becoming in reality, is you don't just look with one waveband, you look throughout using all of these tools, combining them in the best way you can, and that's the way modern astronomy is done. And now I'm going to talk about my first of my three exemplary topics, and this is relativistic jets and spinning black holes. And I'm going to focus in on a topic that has received an awful lot of publicity over the last 2 or 3 years, the so-called black hole shadow seen by the Event Horizon Telescope, this international array of millimeter telescopes making very fine angular resolution images of the central part of a nearby galaxy known as M87. Wait a minute, sorry, I want to go back. I've just done that. I pressed the wrong one, sorry. This was actually the first galaxy to be shown to contain a jet by Heber Curtis, working at the Lick Observatory in California in 1917, over 100 years ago, and he found that this nearby galaxy had what he called a curious straight ray coming out of it. We now see it as a jet, and this jet has bright features in it, but basically it's a continuous flow of energy from the very center of the galaxy, which we identify with a massive spinning black hole. I don't have to tell you what a black hole is, I think you all know, but we'll say a bit more about them in a moment. But this one is a big black hole. It has a mass of about 5 or 6 billion solar masses, 5 or 6 billion times the mass of the sun. So it's a monster black hole in the middle of M87. We see the jet that comes out from the scale of the black hole here, which is about slightly larger than my green spot there. And then you're seeing a ring of gas here, which I'll say a bit more about its interpretation. Then we see, as we get to larger and larger scales, we see a feature that is very common in these. We see edge-brightened emission, and here we see edge-brightened emission here. So what we're looking at is a jet that, in fact, is if Connie is the observer, it's at an angle of about 17 degrees to the line of sight, we believe, that jet, and there's another one in the opposite direction like that. So you're seeing it obviously somewhat foreshortened as it comes towards you, and you're also seeing it brighter because the material in the jet is moving close to the speed of light. And so we see the jet on different scales, like taking a Matryoshka doll and taking it apart, and as we go out, and then this jet itself performs an awfully important astronomical function. It keeps the gas in the surrounding cluster of galaxies. This M87 is near the center of a large cluster of about 1,000 galaxies, a large sort of conurbation of galaxies, and that contains a lot of hot gas, and that is kept hot and prevented from falling inwards by the jets and the outflows from the massive black hole associated with a tiny region no bigger than the solar system in size right at the center of this galaxy. So that's a remarkable thing. It's an even more impressive thing than having a nucleus in the middle of an atom making nuclear power and so on, all that tiny little nucleus in the center of an atom. This is an even more impressive contrast of scales. And so, that's sort of overview of obviously a lot more observations. These jets themselves are extremely common and general phenomenon in astronomy. Just go through this very quickly. Here's a lovely map made by a lovely telescope, I should say, called Meerkat, which, as you might guess, is in South Africa. It's been worked brilliantly, and one of many things that it has done, I'll show you another thing in a moment, but one of many things it has done is it's just taken a patch of the sky and just counted the number of radio sources there. And there's about 2 billion if you sum it up over the whole sky. So if you just multiply, you'll get 2 billion sources. And we think about a half of those, 1 billion, are jets associated with active galaxies. So this is a common phenomenon, 1 billion of these things. Here's the Crab Nebula, which is a famous supernova explosion, happened in AD 1054, and there's a spinning magnetized neutron star there, jets coming out. Here's X-ray emission in blue, and then optical emission in purple surrounding it, and this thing is expanding and so on. The whole thing is energized by a spinning magnetized neutron star. I'll say more about that in the third topic, but there are jets. Here's a protostar, certainly not a black hole. It's something like our solar system might have been in its earliest days, ring of gas with planets forming out of it, and that has jets. The famous one shown by the ALMA telescope. Here's SS433, a binary black hole in our galaxy, a stellar mass black hole in our galaxy, binary. It's precessing on the sky, so it has one jet like that, another jet like that, and it precesses like that in space. You watch it, that's what this shape is here, and we learn a lot about jets from that. It's a totally different type of object. Here's a source that's rather like M87, but pointed more closely towards us. It's got an infinitely forgettable name, and it is claimed, and the evidence for this at the moment is not strong. We're dealing with science in progress, science on the way. There's suggestive evidence, but not compelling evidence. It's associated with neutrinos, and these are the neutrinos that Francis Halzen and his colleague are trying to find with IceCube. Okay, so this is all being opened up. If I give this talk, I hope in 5 years' time, I'll have a much more sophisticated story I hope to tell. And then finally, here's the famous two-neutron star merger that was detected in its gravitational radiation by LIGO Virgo, a spectacular piece of multi-messenger astronomy. The people who were left out at the party were the radio astronomers, and they were told to go home, don't bother, but they were stubborn people, and eventually they found a radio source associated with it, and lo and behold, what has you found? You found jets. So jets are everywhere. Okay, so there you go. So black holes, as you know, became very famous. These are my friends and colleagues here. Here's Ray Weiss, Barry Barish, and Kip Thorne, who were given the Nobel Prize for the development and success of LIGO, and in company with Virgo and other, and Geo 600 and so on. And then more recently, in 2020, Nobel Prize was given to Roger Penrose for theory, Reinhard Genzel using the VLT, which I showed you, and Andrea Ghez, who used the telescopes in Hawaii, to show, as you just saw there, stars orbiting the black hole, the 4 million solar mass black hole at the center of our galaxy, which has taught us an awful lot about the existence and behavior of black holes. I must admit, when I saw this image here, when I first heard about this announcement, and I remember this image here. These are all my friends and colleagues. I was thrilled for them, but my next reaction was, boy, maybe black holes have hair after all. At any rate, think about it. Okay, that's a physics joke. All right, so not only, and this is more what I'm going to be emphasizing here, is not so much the gravitational radiation, but they may also be responsible for the zeta electron volt cosmic rays and peta electron volt gamma rays and neutrinos and so on. Okay? So they're part of the story. So let's move on. Okay, but this was the image, which was, I think, one of the most downloaded images that was in the media from science for a very, very long time, and deservedly so. It was a remarkable accomplishment to make this image. And the person who led actually the whole collaboration was Shep Durleman, and I like to show this picture in Belgium because I just exchanged emails with him about a week ago, and I told him where I was, and he said, I was born in Leuven, so he's one of you. Okay, so he's American, but he was actually born in Leuven. So that's Shep Durleman, and there was some skepticism. I showed this to one of my colleagues, and within about 20 minutes, she sent me back this explanation. She said it's all a fake science and a government cover-up, and so this is what they've actually got. And of course, and there was this, many other jokes like that. But at any rate, but nonetheless, it was a great accomplishment. I'm not saying anything less than that. Not the least, getting all these astronomers to work together. At any rate, so let me tell you a little bit about black holes. And there's of course much more that whole courses that you can give on this, but just what's relevant here is that the main observations by astronomers of black holes, not the febrile imaginings of theoretical physicists who are in a quite different territory. These are what is actually you see out there on the sky. There are in two classes, most of them, stellar mass black holes and massive black holes. And they're fully described by mass and spin, and the charge is effectively zero. One can theorize about charged black holes, but in practice, in astronomical context, they discharge immediately. And so the charge is sort of irrelevant for the black hole. So in that sense, they're simpler than electrons. The mass of a black hole, I'm not going to give the mathematics, but it's pretty simple, is a scale for length and time and energy. The more massive black holes are correspondingly bigger. And they have an event horizon. You all know what that is. And they release gravitational energy, because if we have a star or a gas that's orbiting around this black hole, as it gets closer and closer to the event horizon, it must have lost a lot of energy. And so it can release, using the most famous equation in physics, E equals mc squared, it can release about 10% or so of that energy very easily. And so it makes it much more efficient as a radiator than, say, a nuclear process like in a star. Stars burn by nuclear fuel, and so it releases energy very fast. Now, there was one thing that's very important. Here's Schwarzschild, who first described mathematically, although unwittingly, what a black hole is. Here's Roy Kerr, who knew exactly what he was looking for and found it in 1963. But in between, physicists got very confused about the physics of black holes, Einstein included, but one person who was not confused and got it right from the start was Georges Lemaitre, who needs no introduction here. Another important feature of black holes, understood first by Roger Penrose, and then a key part of the story came from Stephen Hawking, was that a spinning black hole has effectively up to 30% of its E equals mc squared energy there for the taking. It has up to 30% of that energy there can be taken, and and if that's done with a modest efficiency, it's about the same 10% as you get from gravitational energy. Now, the way that Penrose proposed doing this was throwing rocks into it in special orbits, and that indeed works, but it's not something that's going to happen very naturally. In fact, we know it doesn't happen naturally. But the functional equivalent that does seem to be happening, we've now got good evidence for this, is it's a magnetic field that essentially takes, with a 50% efficiency or so, the spin energy out of a spinning black hole. And I'll say more about that in a moment. So I'm running out of time, probably. I won't say too much more about this. So let's go back to that famous event horizon image, the cat's eye, if you prefer, and what they thought they were looking at, and this is the conventional view. Conventional view is that there's a big ring of hot gas here orbiting the black hole, making a sort of funnel from which energy extracted from that funnel creates the jets, the two jets which I showed you. And so that's an outflow of electromagnetic energy from the spin of the black hole, and then the interaction with the surrounding outflow from a disk is what causes the edge-brightened structure that you saw in that black hole. Now, if you think about a black hole as a sort of electrical conductor, just like any electromagnetic induction apparatus, there's a moving magnetic field, if you like, relative to a conductor, and that induces an electromotive force, which in the case of M87 will be 3 times 10 to the 19 volts. You can see why an object somewhat more energetic than this can be making the highest energy cosmic rays. Corresponding currents are about 300 petamps, and now what I'm just going to advertise here, it may come up in a bit more detail in the questions, but I'll just advertise is that I personally, in each of these 3 topics, I'm a heretic in the sense that my own interpretations of what we're looking at are different from sort of mainstream, if you like. And in this particular instance, I think that what is actually happening is that this spinning black hole is not just powering the jets, but is also driving away the gas that's in the ring around it. And so what you actually have in this system, and I say we can discuss it in a bit more detail in the end, is that we have infalling gas, which we know has to be there. It confines magnetic field in this way, but the spin energy of the black hole not only powers the jets, but sends energy outwards through this gas so that essentially all of the gas that is supplied is driven off in this wind here, and this wind is highly magnetized and is responsible for the observed shaping and collimation of those jets. It's a whole system that goes from a scale of 1,000,000 times the size of the black hole right down to the size of the black hole, and it's the entirety of that is responsible for the jet phenomenon. And this is a very different view from that is advanced by the Event Horizon Collaboration people. So here's another image that was made by the Event Horizon Collaboration. It's a beautiful image of a nearby galaxy called Centaurus A, and you can see in 2 of the jets, actually, the jet and the counterjet, and you can see that edge-brightened emission. Remember I said the emission was sort of like from a boundary layer, from an edge. You can see it there. This has just come out a couple of months ago. And here's another meerkat image, just to reassure you. This is an image of our galactic center. What do we think all these lines here are? This is a radio image of our galactic center, and all these features here. these are almost certainly energized magnetic flux tubes. The whole thing has to be magnetized. So we have, I think, really good evidence, and this is a beautiful image, that the central regions of galaxies are full of magnetic field. And that's what you're tapping to make these jets. So that's the contention, and I say we can go into this a bit more. Now let me go on to my second topic. How are we doing for time? I'll just see how we're doing here. Okay, yeah, okay, I think we'll be okay. So, yeah, okay, so my second topic is to talk about the acceleration of cosmic rays, and in particular to focus more on the very highest energy ones. And so here's a spectrum of cosmic rays shown in its entirety from energies less than the essentially mildly relativistic particles, energies less than the rest mass energy of a proton, say, all the way up to the very highest energies. This is what is observed, but what is created is probably more like a zeta electron volt, these enormous energies. Just to give you some idea of the scale involved, here's the Large Hadron Collider at center of mass energy 13 tera-electron volts. A tera-electron volt is 10 to the 12 electron volts, so that's positioned correctly there. Here's Eden Hazard, of whom you may have heard, and more or less any game of sports where you propel a ball one way or another is giving you about 100 joules in that ball. You know, kick it or hit it with something or whatever, it's going to be about 100 joules. That's the same energy of one of the most energetic cosmic rays, and that's a subatomic particle. Think about that for a moment. Don't be frightened of this. If you're not a particle physicist, you can distinguish energy from momentum, and in terms of momentum, one of these cosmic rays has the momentum of a very small snail. But in terms of energy, it's the same energy as a well-hit soccer ball. Okay, and this is what you see when they hit the atmosphere. They make giant air showers, which are, you see the consequences of this with telescopes like Auger. And they also are important because they create and destroy life, as anybody who wants to live on Mars will discover. And so let me just give you a little bit of the story of cosmic rays. They are the ones that energies up to about a peta-electron volt, 10 to the 15 electron volts, are believed to mostly originate from supernova explosions that happen within our galaxy. So a supernova explosion, and mostly of massive stars, and they send this gas out at enormous speed, 10,000 kilometers a second, the speed of light, and they create shock fronts as they move outwards. A shock front is a discontinuity in the gas flow. We have gas coming in with high speed and leaving on the other side of a surface with smaller speed. So what we have is gas coming in at high speed, going out the other side at slower speed, and so that means that the gas on this side is actually moving towards the gas on that side. It's like a traffic jam or something. And so what can happen then, and what we believe does happen, is that it scatters on one side of the shock front. By that I mean little magnetic inhomogeneities, magnetic waves. They scatter the cosmic rays, interact with the particles are scattered backwards and forwards across the shock front like a game of tennis, and these are approaching each other. So if you've got two scatterers approaching each other, the cosmic rays are going to get energy. And when you go through the statistical mechanics and astrophysics of this, it looks like it can really explain how 10% of the supernova energy goes into a parallel distribution of cosmic rays up to peta-electron volt energies. So that's the sort of standard story. And they obviously have many other functions. However, we know, and I just like to throw this in here just to emphasize this discovery space action. These are very recent observations within the last 6 months, mostly in using high-energy gamma rays, the highest energy gamma rays, using here 3 different facilities, Hawk in Mexico, and then 2 in China, Tibet, and Lasso. And it looks like in our galaxy, we actually are seeing the sources of electron volt cosmic rays through the secondary gamma rays that they're creating. So this is all hot, you know, like most of this has happened over the past year or so, and it's pretty exciting time in this business. So moving on, now if we say, well, what about the cosmic ray particles between a electron volt and the higher energies? If we go up to, say, about 100 times that electron volt scale, then what we think is going on is that another shock front, and here I'm sort of going out on a bit on a limb because not everybody in this business agrees with this. They have alternatives which may turn out to be correct, but essentially, what I meant to do is go back, sorry there. What you have is an outflow of gas from our galaxy, which we do believe exists, and it goes outwards. It too forms a shock front, and that shock front does the same trick as the supernova shock fronts, but at higher energies, and you can take particles and take them up to higher energies, and so that can get you up to 100 electron volts, say, or maybe even 1,000 of those. And in particular, it does this for heavy elements, which the cosmic rays are do seem to be composed of at these much higher energies. So here's the sun in our galaxy, here's the whole galaxy, and it has a shock from this outflow of gas. That's where you get these higher energy cosmic rays, we claim. And all galaxies, all of those trillion galaxies we've got in the sky are essentially doing this trick and filling intergalactic space with high energy particles. But they're not explaining the very highest energy particles. And for those, the invoke is an even larger shock front, and this is the shock front associated with a cluster of galaxies like the one in the Virgo, round M87 that I told you about. This I like to show at this time of year. It's the Perseus cluster, and it has my second recognition of Halloween, because this kind of looks like one of those Halloween pumpkins shown there. But it's actually the hot gas in the center of the Perseus cluster, observed with an X-ray telescope. And this is going to be attracting gas from the intergalactic medium falling in, and that will create a shock front, just like the one I told you with the supernova elements, but inside out. It's just the same sort of thing, but inside out. And that too can accelerate particles. And the contention of my colleagues and myself is that that is the source of the very highest energy particles. If you don't like that, try the jets. That's another good idea. That may work as well. Got it. Okay, let's move on. So this we think of, I should say here, as a hierarchical model where the lowest energy cosmic rays from the galaxy get pumped up a bit more by the termination shock, which get pumped up a bit more by the, a small subset of them get made into the very highest energies. Now let's finish my final topic, which I will go through rather quickly. And again, this is probably the most interesting from a physics point of view, and we can perhaps ask questions about that. So we're going to go to the fast radio bursts and the magnetars. So basically the phenomenon, and it was discovered actually by a graduate student about 12 years ago, and they're little flashes of radio pulses lasting intrinsically about a millisecond. We now know that they happen about once a minute over the whole sky, and they're cosmologically distant. They're highly polarized. They're rather distinct. Some of them repeat. Some of them now, and this again is two new discoveries, that they show periods of days, which mean, as Connie will recognize, the binary system probably, but they also are showing periods on the scales of 100 milliseconds. And if that's true, well-defined periodicities, that has amazing implications, which Connie will also recognize. So these are a lot going on right now. This is sort of intense time of discovery. Theoretical physicists got in the act early on and helpfully provided a long list of explanations of what's going on. And here, the most embarrassing of all was the microwave ovens, because it turned out a lot of these happened at lunchtime, and it turned out one of the radio observatories had a microwave oven that was leaking, and you can't imagine how embarrassing that is. But, you know, the alien light sails, take your pick, quark nuggets, entangled molecules. The amazing thing about all these explanations is not that none of them were right, but that all of them were published. But at any rate, more seriously, there were active galactic nuclei, supernovae. All of these were more sensible and more mainstream astrophysics. Pulsars were also explained. I'll go into that in a moment. But magnetars are now regarded as the favored explanation. And I have to say, this is what from day one, I thought that was what they were. And I feel a little sense of vindication. And I'll explain what a magnetar is, but first I must tell you what a pulsar is. Those who believe in democratic science should say that every explanation is going to be right for one burst, but I don't really believe that. Okay, so a pulsar, before I tell you what a magnetar is a spinning magnetized neutron star, about a solar mass, 10 kilometers, field of 10 to the 12 Gauss, or 100 megateslas if you prefer, spin periods of milliseconds to minutes, and they make radio and gamma ray pulses. They're magnetized, they spin on their axis, and they're like a lighthouse and make pulse, 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 pulse. So let me go on, and the energy for all that they do, including in the Crab Nebula, comes from the spin of the neutron star, just like I invoked in the black hole. Okay. The magnetars are about 1% or maybe 10% of these neutron stars when they're young, in the first 1,000 years of their life probably. They have 1,000 times larger magnetic field, 10 to the 15 Gauss, 100 gigateslas or thereabouts. And this is over the limit for regular quantum electrodynamics. This is beyond the Schwinger field, and you're taking quantum electrodynamics into new many-body non-perturbative territory. It's very exciting. People are trying to do experiments with this, and I'm part of some of those, and it's a very exciting business. Now, one of these fast radio bursts has actually recently been identified. It's a very weak radio burst, not a proper one, but it's been identified with a galactic magnetar, and that has persuaded most people that a large fraction of these objects really are magnetars. So what do we think is going on here? And I say there's a lot of perfectly good explanations out there. I'm going to tell you what my particular story is, and we'll see whether or not that has what realms of truth it has, because a lot of this is highly distinguishable observationally. I like to describe this in the Aristotelian way of earth, air, fire, and water. And so it starts with a starquake, probably something now in the interior of the sky. And that when I said there were 100 millisecond periods there, that I suspect is a quake, a wave going around the neutron star. We're doing astrology, as you would call it. And so what that does then is shake magnetic field around. And this magnetic field is going out in a magnetosphere, going as 1 over r cubed, carrying the same amount of energy, but as it's getting weaker and weaker, the waves are getting stronger, just like Indiana Jones and the bullwhip, which becomes supersonic at the end. This moving magnetic field, of course, makes a lot of lightning and makes a lot of electrical discharges, so it's very easy to make electron-positron pairs. But the net result of all of this is that you make this sort of what I like to call an electromagnetic tsunami going out into the magnetosphere. And this is initially made with a scale of about a kilometer, but I'll just give the punchline here. It looks like there are instabilities which create that to the centimeter wavelength radio waves that are actually observed by the radio astronomers. And so there are many explanations being actively explored. Here I've just sketched, and I can go into this in a bit more detail, what my particular version of an explanation is, and we'll see how that works out probably over the next 5 years or so, as a lot more is going to be learned observationally. So just the final thing here for the cosmologists here, not only are these fast radio bursts, like the pulsars themselves, very, very interesting in their own right as sources and as exemplars of extreme physics, they're also useful. And in particular, these fast radio bursts are going to be very useful for probing the hydrogen out to large cosmological distances, and also the gravitational potential wells. You'll see lots and lots of lenses and so on and so forth. So this is a very exciting business, and they're going to be useful as well as sources. So if I just go on to the end here, so this is a sort of, if you like, a quick six-line overview of what I've said. I've slightly overstayed my welcome, but at any rate, I'll stop at this point. Thank you very much, Connie.
Okay, I'm here. Thank you, Roger, for this overview of many extreme astrophysical phenomena. And I am turning the floor to the audience if they have any questions. And I particularly encourage young students to ask questions.
And I particularly encourage those who are going to give me some answers, because I've got a lot of questions too.
Who has the first question? Okay. You're not a young student.
Always a student. Yeah, I was just wondering, the last part of your talk, when you were talking about these radio bursts, you said they are everywhere the whole time, and they were only discovered 8 years ago. So well, where were they before? Why didn't nobody see them before?
Well, they were discovered in a search for, it usually happens in astronomy that people are vaguely looking for something else, and when they discover something big and important. In this case, it was primordial black holes and so on was one of the things they were looking for, and this assuredly is not primordial, exploding primordial black holes. There was the advisor told the student to go and look through lots and lots of data to see if he'd find any pulses. And the student dutifully did this and found them. And then almost all of them were interference. Okay? That's what you get with the radio telescope nowadays, is interference. However, some were different. And this is why astronomers are good at this sort of stuff, is that they tend to pick that sort of stuff. They tend to smell that out, and they don't stop. They worry about it, and they go back and try. And it turns out a lot of it was sort of spurious stuff. But in that set of radio bursts were some that are absolutely clearly cosmic sources. Just like happened with the pulsars. You know, it's easy to think pulsars going pulse, pulse, pulse. Lots of things do that. But the real pulsars were cosmic sources. And the same thing happened here, and it was a wonderful discovery. And, and it's, and a reward for persistence. And we now see them, we're finding them very, very fast. And there'll be many millions of them before long. And you can do statistics with that big time. That's why you can do these for cosmology. So, yeah. So, I mean, it's really because people expected interference. Sorry? You can see them out to about a redshift of 1. We know from the so-called dispersion measure what the distance is. So it's about the most distant about a redshift of 1. But before long, you're going to see some breathlessly exciting announcement that somebody's found one at redshift of 3 or whatever. That's going to happen.
Okay. Ronnie?
Thank you very much, Roger, for this wonderful overview. I share the same enthusiasm as you because, well, all of the topics somehow touch on plasma physics and on magnetohydrodynamics, and we all like to do that. Mm-hmm. But it's just focusing on that 5% the cosmologists tell us. So what is your, let's say, frank and open view on all the stuff we don't understand? Can you say something about that?
Are we talking cosmology here? You're accusing me of baryon chauvinism, aren't you? Okay, yes, I'm a baryon chauvinist, yeah. But I'm also, in my spare time, I try and think about cosmology. And as you know, there's 6 times as much dark matter out there. And astronomers have done a splendid job telling everyone what it isn't. Then experimental physicists have done even better telling them what it isn't. And we don't know what dark matter is, but we do know it's there. And it is dumb and stupid and doesn't sociopathic. It doesn't interact with anything except gravity, as far as we can tell. We see no evidence for that. And far, far away, the best evidence that it is there comes from observations of the cosmic microwave background. If you look at the cosmic microwave background, you get these spectacular spectra of the intensity fluctuations and the polarization, fitted by a simple physics model using mostly 19th and early 20th century physics, nothing particularly exotic, and 6 parameters. This dark matter is as advertised. So so it's a really good puzzle, what it is. It's one of the best puzzles in physical science out there. And my personal view, and I'd love to be wrong, because people spend 10 years of their life building experiments and so on, is that we'll find out what it is by the side. Scientific discovery doesn't happen when you walk through the front door. Somebody crawls in through the side window, and it'll be something. People looking for something different will suddenly get a clue, and they will figure out what it is. And the right sort of strategy, I think, in terms of searching for it, is to try lots of sort of relatively cheap experiments. Try many relatively cheap experiments. Hope that you find something. And in particular, the ones that develop technology are well worth pursuing. So I'm sort of an optimist that we'll find out, but through experimental physics, including especially at the LHC, and also all the astronomers have done, we don't know. So that's the dark matter. And then there's the 69% of the dark energy. And this gives me an opportunity to praise Lemaitre, who we've seen called out in this exposition, just this lovely exposition and so on, because he essentially, he was by far and away a long way ahead of his time, thinking about the whole business in a very modern way. And there is evidence that there is something that very close to what Einstein introduced in 1917, the cosmological constant. Now, my personal view is, again, you asked me to speak as my personal view, not that I'm saying this is proven or other people agree with this, is that it is a cosmological constant. A lot of effort has gone into testing and proposing sort of phenomenological alternatives, which seem to me quite distasteful, and introduce sort of elements like preferred frames and so on, which I find rather unlikely. The cosmological constant really, if you look at it the right way, comes along with general relativity as one number. And so once there was good evidence that it really existed, and it wasn't a new discovery. As I said, Lemaitre was there, Einstein was there, and then he got misled by himself, but he made mistakes and so on. But Lemaitre understood, and then the first book I ever read on cosmology was written in 1952. Flat lambda CDM is there. It's just all worked out. The equations people use today, it's all worked out. It was always part of the background. Now, it's a puzzle for particle physicists, and I sympathize with them. It's a genuine puzzle for particle physicists, and to understand where it comes from. And what I would offer for that sort of metaphysical question, if you like, is that maybe the natural approach of physicists, and especially of particle physicists, of reductionism, of saying everything depends on something smaller and more energetic, is failing us here. We shouldn't necessarily be forcing the sort of round peg of general relativity into the square hole of quantum field theory. And in fact, maybe the cosmological constant is our first glimpse of physics on the very largest scale, rather like the photoelectric effect, photons and so on were and specific, black-body radiation and so on were the door to understanding the physics on the very smallest and highest energy scale. So that would be my off-the-record, not off-the-record, answer to your serious question, but you'll get very different answers from different people.
Okay. Johnny?
Okay. You mentioned throughout your talk quite a lot of times the influence of the magnetic field, and especially quite extreme magnetic fields, including magnetars. What is your take on how to actually generate such, extreme magnetic fields, and how can we produce them physically?
Yeah, again, a really good question. Not only am I a baryon chauvinist, I'm a campo chauvinist too, and I think that magnetic fields are really quite pervasive. They're all perverse too, but they're quite pervasive, and they're responsible for an awful lot of what we see. How are they made? Again, there's a school of thought that say that there's a connection to cosmology, and you can think about first-order phase transitions, particularly at the electroweak scale and so on, that might have actually generated the very first magnetic fields. To me, that could have happened, although I think it's in practice, if you look in a bit more detail, it's rather hard, but I think it's almost irrelevant. Essentially what happens is the very first protostars, as soon as you've got ionized plasma there are mechanisms, sometimes called the Biermann battery, but it's much more general than that, that will make magnetic field large enough to make the Larmor radius of a proton, say, smaller than the scale of the system. That gives you a start, and that will make magnetic field where there was none before. As long as you've got electrical charge, you'll make magnetic field. And there are natural mechanisms for doing that. Then you take, that's called sometimes a primary dynamo, then it becomes a secondary dynamo, and that's when you get mechanisms that take a magnetic field and turn it over like that. So the field then grows exponentially. The rate of change of the magnetic field goes as the strength of the field, so it grows exponentially. So it then becomes so big that it becomes dynamically important. Meanwhile, as I showed, those protostars, and there are other ways of doing this, but the protostars are the easiest one to think about. Those protostars are making these jets, so they're polluting their environment. They score very badly in Glasgow. They're polluting their environment with magnetic field out to tens or hundreds of parsecs. Then the galaxy, with all of the supernova explosions and all those sort of things going on, the winds that it makes, then pollute intergalactic space. And the big jets and radio sources do the same. And so before long, you've got magnetic field everywhere. And so I like to say wherever there's iron, there's magnetism. And so that means where you see heavy elements in intergalactic space, you almost certainly got magnetic field there too. So for me, it's almost, I would be much more surprised if there were no magnetism than if it's everywhere. And I think astrophysical processes like the one I just outlined are the ones that are probably leading the charge, and it happens early in the life of the very first galaxies. The particular, the particular sort of choreography and details of that is certainly to be done, but I would look much more to there than I would look to exotic phase transitions in the early universe, even though the second option is more interesting.
Thank you. One final question by students.
So if it's all about these magnetic fields and charges, how could a charge of a black hole have any influence on the magnetic field and charge and all that? Or how are we so sure that we can always neglect the charge of the black hole?
Okay. Yeah, again, I'm really glad you picked up on that. You noticed, and I glossed over it, so thank you. And what I'm about to say, there's a minority of my colleagues who would disagree with it, so there's the government health warning. Okay, so having said that, basically what's happened, let's see, there are solutions of Einstein's field equations in their classical form for charged black holes. They're called Kerr-Newman for spinning black holes, and they're perfectly reasonable solutions to the Einstein-Maxwell equations, which means to say you get the GR right, and then you add in the magnetic field, and that magnetic field and the charges are gravitationally important. They are applied mathematical solutions, and there's not a problem with them as long as you don't make the charge or the spin too large, then they're perfectly fine. The problem is that if you take M87, we've got, say, 10 to 100 exavolts of potential difference. And these magnetic field lines will have electric field lines associated with them, and they'll make an angle. So there will be a component of electric field along the magnetic field. And that potential difference in these solutions, as I say, would be 10 to the 19 or 20 volts. Okay, I'm going to the extreme case. You know that you only need 1,000,000 volts to make an electron-positron pair. 2½ MeV, that's all you need. Now, in practice, you need much more than that. Under astrophysical conditions, this is an issue of practical astrophysics, not theoretical physics, but under practical astrophysical conditions, to make a discharge happen, you need about 10 to a teravolt, or about 10 to the 12 volts. You still 8 orders of magnitude less than the voltages you've got available. So my contention is that under essentially all of these astrophysical black hole environments, you discharge the charge on the black hole essentially instantly. It's like the cumulus cloud above the church steeple. You know, you just have lightning strokes and you just discharge the cloud. You know, more than 30 kV per centimeter, 30 kilovolts per centimeter, excuse me, or something like that. It's well known how you discharge things, and it will happen here easily. And the only interesting question is which QED process kicks in first. So for that reason, I think these black holes, they have charges, but they're gravitationally insignificant, and they're no different from the charges that exist on neutron stars. So that's what I think actually happens, and what the way the magnetosphere is described, both in the pulsars and in the black holes, and the magnetars as well, is you have something that's called force-free electrodynamics, which adds enough charges and currents to keep the electric field perpendicular to the magnetic field, so there's no potential difference and no need to create any more charges. And you only need a tiny number of electrons and positrons to make all of these giant, 10 to the 17 amps flowing out. It's only a tiny number of electrons compared with what you've got available to make that. So that's the way I think it works in practice. And so thanks for noticing that and picking up on it.
Okay, well, with that, I think we should wrap up, because there's also still a nice meet and greet time for students, but let's thank Roger for this wonderful overview talk.
Thank you. Thank you.
So now I am asking all those who are not students to leave. And except for Marina and Roger, they will stay with the students.
But including Alex.
To hold the chats. I'll drag Alex along with me, don't worry. Yeah.